To begin with our operating system development journey, the first step that we need to do is to build a bootloader. Okay, to basically start our operating system from scratch, something needs to be there to load it from the ROM. Okay, so that part is taken by the bootloader. Okay, so our system will be a x86 based system, like we discussed. It will be a microkernel, and for that the bootloader across all this like different types of operating systems remains the same. Okay, and there are different new strategies like multi-stage bootloaders and stuff do exist, but today what we will be building is just a basic bootloader. Okay, just to get a gist of it. So as to begin with the coding part. Okay, and it will be like we'll refine this thing over the period of the development. And to begin with, a few prerequisites or things that you need to install. Okay, so first thing that you need to install is network assembler or NASM. See this thing. And another thing is the QEMU or the emulator for x86. Okay, so we'll be building it for x86. Okay, this is the Intel architecture, so you need these two things. After you have installed these two things, obviously I have already installed in my system, what we'll do is we'll start writing the code. Okay, so first we'll write an ASM file or the assembler file. Okay, so I'll call it bootloader.asm because it is a bootloader. Okay, so first things first we need to remember is we have to set it as a 16-bit program. Okay, so in Intel architecture, basically x86, there are two modes. One is the real mode. Okay, in the real mode you have like 1 MB of addressable memory, and another one is the protected mode wherein you get up to like 4 GB, and now it has extended to like billions of GBs like on paper. So that is available. So for now every Intel device boots through the real mode itself. Okay, so how we do it is like first we tell the assembler, so this is the assembler directive basically, to keep this program as a 16-bit real mode program. So this is necessary. And now the important part that we need to do is we need to set the origin, okay, from where this program will start. And this is something that is dictated by the hardware vendors itself. So BIOS, all types of BIOS, specifically targeting to like the Intel architecture, have this predefined address of origin, okay, where they pick the program from, and that is 7C00. so this is a little endian address. Okay, and now we actually start the program. Okay, before we start the program, let's just write the message and stuff that we want to display. Okay, so in this program what we'll do is we'll simply write our message. Okay, so that will be hello from hello from microkernel bootloader. Okay, and here we'll write this and another message that we want is to say, because like I said, there are like multiple stages of bootloading, so this is only our first step, so we'll be writing stage 1 OK, and here we write the address. Okay, so this is just a what do you call a message. This doesn't impact your program anyway. Okay, so it's just a message. And remember to terminate the message with a 0. Okay, and for now we'll keep this part as it is. Okay, before we end this program, we need to add a few things to it by the end of it, but for now we'll keep it empty. Okay, so now to begin with we write, so you can place some kind of indentation you can have. So this function clear interrupt, before we actually start anything we need to clear all the interrupts first. Okay, so that if there's any service routine that might be already running or something like that, then we can cancel it out and run our program. So we use CLI first, then we do XOR the accumulator, okay, or the AX. So why we do it XOR is like whatever value will be there, it will be set to 0. So XORing any value with itself returns 0. Okay, so here we do XOR, and what we do now is set all the segment registers to 0. So data segment, extra segment, stack segment, everything is set to 0. So this way we write for DS, ES and the stack segment. Okay, so everything is set to 0, and after that we set the stack pointer to point towards 7C00. Okay, stack grows downwards. Okay, so remember that. Now it is not necessary to remember that, because we will not be using anything as such from the stack as of now, but in the upcoming program, as we get to like multiple stages or something, this might become relevant. So here now we re-enable the interrupts. Okay, so after that, first thing we need to do here is, now that we have set to the origin, okay, everything we have set, now what we need to do is we have to print this thing. Okay, so this address, it will go directly, okay, like the 7C00 address, and from there it will start the execution based on the start label that we have given. So what I need to do here now is I have to take my source index and point it to the MSG or the message that I want to show. This message, hello from Microkernel Bootloader. Okay, and that stage 1 running at whatsoever address it is. Okay, so now what we do here is we give here a small label, we'll call it a print loop. Okay, so here what I do is I load byte this thing. So what load byte basically does is, this register you see AX, so this AX register is made of two parts. One is the AH and one is the AL part, lower pair and higher pair, 8-bit each. Okay, that forms to be a 16-bit AX. So what happens is, like, your AL points to source index, the location pointed by source index. Okay, and after that, at every increment, so here we have loaded this thing and it will load byte wise. Okay, so 1 byte we have loaded, then we check whether that byte is 0 or null terminator. Okay, in this case, if it is, okay, if it is a null terminator, then you get something called as a 0 flag, which is set. Okay, so there are flags in the system which are set, and based on that we can do conditional jumps over here. So for that we do here is something called as jump if 0. Okay, and from here we jump to the end of our program, hang. Okay, so this is a jump that we want to take for our program, so that also we'll only define, okay, in the upcoming part. So what we need to do is, just in case the number here is not null terminator, so every the byte that we are incrementing over here, we are checking whether it is the number or not, that is the null terminator or not. So if in case this jump if 0 doesn't execute, then what we need to do here is we need to move to the next instruction, which will be the BIOS interrupt. Okay, so this interrupt will display the data on the screen. Okay, so this is called teletype function. Okay, basically the interrupt, video interrupt it is, so it is called 0x10 interrupt. Okay, so that what it does is like prints a single character onto the screen. Okay, so for that what we need to do is we need to set the value of AH to 0x0E. Okay, so this interrupt thing is like a fixed set of interrupts are available. So for that you need to set the values of AH, AL and any other registers that you require, and then you call the interrupt function. So for this thing we need to do two things over here. First we need to set the interrupt into the higher pair. Okay, so AL already has the data which is to be displayed. Okay, and this BH we set to the page number 0. Okay, so this is for like the exact what you call the rendering part. So for now we can keep it page number at 0. Okay, and finally the interrupt. Okay, so 0x10, the BIOS video interrupt. And now what we do is we simply loop it back. So now it is pointing to the next character. Okay, let's just jump to print loop. And now this print loop, after this print loop, here we will write the hang function, the hang label, not the function, sorry. And here in this label again we'll clear the interrupts, then we simply do halt. Okay, so this will like cause a non-maskable interrupt or that sort of a thing and end it over here. And just for the safety of this thing we'll add a non-conditional jump. Okay, irrespective whether any condition happens or not, it will jump back to hang. So this is like a closed loop running around for this thing. Okay, so this was our program. So the actual magic of this program is not in this part that we have written. So this is just a function to the display like whatever the message that we have. Okay, so how does actually the image get picked? That is done by MBR padding and boot signature. Okay, so what is exactly MBR padding? So all these devices that we have something called as master boot record. Okay, so whenever you plug in your pen drive, your CD or any kind of media device, so how does your operating system or the computer know like whether that device is bootable or not? So sometimes you get that error, the device is not bootable. So this thing is decided based on this marker, or what you call it, something called as a magic boot signature. So this 512 byte partition is something, or the sector basically is the one that helps us identify whether that is a bootable disk or not. So how it is done is we use a directive called times. So what it does is here we write 510 because like I said 2 bytes are for the actual signature, magic signature, which is AA55. Okay, so those 2 bytes we keep aside and our program we are taking. So here we write dollar minus double dollar. So what it does is it calculates the offset. Okay, so it will pad those remaining bytes with 0. Sorry. Okay, once that is done, we have our signature, that is our word. Okay, which is 0xAA55. Okay, so after that we can save this thing and we can start the terminal over here. Okay, so now I have already installed the assembler or the netwide assembler. So we'll compile this thing, not rather compile, we'll assemble this thing. Okay, so while assembling, a few things that we need to remember is the format. Okay, so usually you might have used this netwide assembler or not, I don't know, but usually people use something called as ELF formats. Okay, but in this case what we need is the flat binary format, because we are loading it from this thing. Without header we need it. So here the important option is using this -f bin option. After that you write your file name bootloader.asm and the output file name, you can say, okay, which is the bootloader.bin file. Okay, once you do this thing, okay, line number 14, okay, sorry, my bad. Sorry, so these are labels, so usually I forget this thing. So these labels need to have colons after that. Okay, so that is something that was missing. Now it is fixed. So once this is done, what we need to do is, now we load our binary file. So this, you can see here, a file is created, bootloader.bin is created. What we need to do is, we need to load this file. So how we do that is, we write qemu system, and here we write i386. okay, so this will give you the i386, and here we use the option drive. So this will be like this binary file will be added it like a external drive or a image or that sort of a thing. Format we have to keep it raw. Okay, and why it is raw? Because it is a boot image, so that is why. And finally the file that we want, which will be the bootloader.bin. okay, and let's just see if that works. Okay, my bad. Okay, yeah, so see here, you can see here, this has given the message booting from the hard disk or the device that is there, and this message is displayed, and this is now running directly as a bootloader. Okay, so this was just a preliminary introduction to how this primary bootloader or a basic bootloader is written. In the upcoming videos we'll be seeing like how multi-stage bootloaders and stuff really work, and then we'll be actually starting with a kernel code directly. So we'll not be initially implementing the bootloaders, okay, the multi-stage bootloaders and stuff. We'll be rather implementing the operating system first. Okay, and then after we get to like the base level kernel, like initial booting part, like initial parts of the kernel, then like the clocks and stuff, after that we'll connect it with the bootloaders. Okay, so we'll write separate bootloaders like multi-stage bootloaders, and then we can connect them. Okay, hopefully this might be helpful for anyone starting their journey in operating system. Thank you.